how much our interest we have, passion we have to do something very high technological advances, it is important that we should have the clarity of the basics, and this FTP being an introductory level should be targeted to answer those fundamental doubts of yours. Kindly use the next few sessions till the next all sessions to clarify all your doubts. In case you have more doubts and it is not cleared because of time restrictions, we will take back your questions. We will answer you. We will make sure that the team answers all the questions of yours by the time the FTP or even 1 2 days after that. Okay, so kindly pay attention and then learn as much as you can. This is our interest. So with this few words, I would like to introduce our next speaker, Dr. Praveen Meduri. Dr. Praveen Meduri is an associate professor from Department of Chemical Engineering, IIT Hyderabad. His research focus is on photoelectrochemical water splitting, solar fuels, metal ion, metal sulfur, metal selenide batteries, carbon sequestration. He has authored more than 30 publications and he has one issued patent. He is one of our dynamic young colleagues, and his research group does a lot of innovative works on various catalysis related activities. So he's the right person to give this particular talk on introduction to energy storage. Over to you, Praveen.
Okay, thank you, Santosh. I think thank you for the introduction. So, am I audible? Hello.
You're audible. Yes, yeah, you're audible.
Okay.
Yeah.
Okay. So let's get started. So what I'm trying to do, or what I will be doing in the next hour and a half or so, is to try and go in depth into what Professor Pillai has already introduced. So he has talked about several things in his presentation, and he gave us a very good overview, very dynamic overview of where things stand and where things are moving. So what I would like to do, I think, is to go a little in depth into some of those things that he was talking about and kind of refresh the memory, which will essentially set you up for the next 4 days. That's what I would like to achieve in this session. So I'll again give you a sort of an overview, but this might be more inclusive of all the different technologies that are out there, and then maybe a slight, maybe a brief introduction on each technology to kind of get you started. And then, as we go into days 2, 3, 4, and 5, I think we'll have a more in-depth, rigorous analysis of the same. Okay. So what we'll be going to talk about is energy storage systems. So we'll discuss a little bit about fossil fuels as well as renewables. So fossil fuels is something that we cannot do away with in the next 20 years at least, or I would rather say in the next 50 years. So I think they are there to be around. So we need to get an understanding on what they are or how they function, and be able to improve the efficiency further. So I think that's one aspect that generally gets lost when we are thinking about renewables and energy storage, more advanced technologies. What we tend to generally ignore and forget is the technology that is existing already. So in that context, I think fossil fuels are also something that you can look at, possibly to improve the efficiencies, possibly to improve the output, energy output and things of that nature. So going into detail, the second part is like more fossil fuel technologies, their benefits, challenges, whatnot. So we'll cover those. Then the more advanced technologies are what we are all excited about for the next 100 years, I would say. So that would be renewable based technologies. And where do energy storage come in? Why does it come in? I mean, why can't we just use this solar cell and be okay with it? So the idea here is to see how energy storage systems support several of these technologies, let it be fossil fuel technologies or renewables. So I'll get there with the apt examples to kind of show you why it is important and how it is important. Okay, moving on. So just a basic thing, just a refresher that energy. What is energy? So we keep using energy, right? So every time we talk about energy, it's just an ability to do work, and there are different units by which you look at energy, BTU, joules, whatever, whatnot. So very basic in nature, and there are different forms of energy. So if you look at the energy storage happening in the nature, there are different forms it can store in. Chemical energy, typically energy between the bonds of the molecules, thermal energy associated with the heat of the object, potential kinetic, electrical energy with the movement of electrons, and then radiant energy is nothing but the energy from the sun, and then nuclear energy is nuclear atoms, energy that you can essentially extract from atoms. And just to get you started, a simple just to put things in perspective. So if you look at one piece of bread with some butter on it, that typically contains about 315 kilojoules. Okay, so that's the energy contained in that buttered bread. So if you just want to put it in context and think about what you can achieve with that kind of energy, essentially is that you can um, okay you can jog for 6 minutes. So if you go out for jogging, so I think that can keep you for 6 minutes. If you bicycle it, you would be about 10 minutes, and walk briskly 15 minutes. Sleep also requires energy. Your body is still functioning, so it requires energy, but at a much lower level. So it's 1.5 hours. And if you're trying to use a car with that energy, it will only last 7 seconds. Yes.
Sir, sorry for a disturbance. Sir, your slides are not visible, sir.
Oh, really? Okay, let me just check.
Yes, sir, we are able to.
Yes.
Sir, it's visible, sir.
It's visible, sir.
Okay. All right. Okay, let me go.
Previously, it's
Now
visible.
it is okay.
Okay, so going back. So like I was saying, so if the same amount of energy, you can only run a car at 80 kilometers per hour for about 7 seconds. And if you're using it to light a 60-watt bulb in your home, it will last about 1.5 hour. Again, it's the very similar to what your sleep is, the energy required. So essentially, this is just to put in perspective that the energy required. So I think running a car, for example, requires a humongous amount of energy. So as you can see it from here, just as an example. So we will go into energy storage systems, some of them of fossil fuels. So I like to call these or refer to them as uh, generally natural energy storage systems. That's how I would refer to them as. And so if you look at different types of fossil fuels or energy storage systems that are available today, include coal, natural gas, you have crude oil, you have wood. You see a lot of times wood being burnt, right? So then you have nuclear. So the image here that is being shown here essentially is a nuclear power plant. I'll also so this is a nuclear power plant. So I'll also come there. We'll just quickly talk about that when we get there also, why it is important, or how India is playing a role in the same. And then sun, so as you all know. So first going into a typical coal plant. So what happens in coal? So you have coal that is being extracted or dug up from the earth, and coal has a lot of impurities, you say. So it can be good coal, or they generally refer to it as high efficiency coal, low efficiency coal, and things of that nature. So one of the messages here is that India has generally deposits of low efficiency coal. So a lot of the coal that is available in India is not very useful, or not very efficient for power generation. So that's the reason India imports a lot of the coal from outside countries, for example Australia, and so on and so forth. So what happens with that coal? So you take that coal, you essentially purify it. So whatever the impurities are, you try to remove them. And then you burn the coal. So in this burning process, what you generate is heat, and the heat converts the water into steam. Steam drives a generator, and essentially that's how you collect your energy. So this is a typical, the image here shows you a typical setup of a coal plant. So this AB, this is the location from where coal is coming in, and then it is being burnt here. The water essentially is goes in. So this is a regular water, and then it becomes steam, right? And then the steam leads to electricity generation, right? So that is what happens. And then once the steam is used for driving the turbine, it comes back and condenses into water. And then whatever is remaining after the pulverization, what you get is essentially waste material. So this is a typical coal process. This has been done, coal gasification, etc., have all been done for hundreds of years now, several, maybe a couple of centuries now. People have been working on it. But we'll come back to that. So that's the general coal-based technology. The second one is crude oil. So we know this, I think crude oil has a lot of uses. So I just wanted to point that out here in this picture. So if you look at crude oil, so this is a distillation column. You can think of it as a distillation column, a simple fractional distillation. Okay. So what it gives a lot of different compounds. So one of the first things it gives is LPG. So we use it for our cooking needs, right? So it's typically LPG, if you see, is a mix of propane, butane, primarily propane and butane. Oops. Okay, so and then the second part is where you get, fuel gas, and some of the other organic compounds like toluene, benzene, and all that. So there's a reforming that happens in one stage. The next stage would be, things like kerosene, diesel, and petrol. So you extract all that from there. And the next one is something called furnace oil or heavy oil. Okay, so it is also, it doesn't have as much energy content as these other compounds or components. So it is used in fuel. So its energy density per weight is very high. So you don't want to use it in other applications, but in a ship, it's not a big concern. So what happens is heavy oil is used in ships for various energy generation purposes. And then last portion is, bitumen, something that is used in, a lot of road making, roof making, etc., etc., etc. So this is also very widely used. So if you look at a typical crude oil extraction process, so what you end up seeing is that it has a lot of uses. So, and then I think this figure doesn't have it, but one of the main or the most value added thing now for crude oil distillation is actually polymers. So polymers was started off as a byproduct of, crude oil distillation, and now it's one of the most value added products. What I mean by value added product, it fetches the most money. So if you look at a lot of these companies like Reliance and others, I think they make more money of the polymers than anything else. I know the other one of the arguments is that we are trying to move away from polymers. Yes, agreed. But as it stands today, since we are still using polymers quite a bit, the idea is that when you're taking crude oil, every single component of crude oil could be utilized somewhere or the other. So that's one of the main reasons why it's very hard to move away from fossil fuels. So 100%, you can say that it's used 100% effectively in some form or the other. All right, so that is about crude oil and some context on crude oil. So then natural gas. So this is something that has picked up in the last century, not century, but last decade or 2 decades. So what is natural gas? So I think it's simply put, it is methane. Okay. So that is nothing but CH4, methane. So natural gas, why is it so enticing is because natural gas, so the simple reaction by which you can produce, so let me write it here. So if you have CH4 plus oxygen, if you burn it, essentially what you end up getting is CO2 plus 2H2O. Okay, and excuse me. Hello. I can. Somebody, there is a lot of disturbance. Can you mute it, please? Hello. Hello. Can you guys hear me? Hello. Can somebody please respond and say whether you are able to hear me or no?
Sir, we are able to hear you, sir. You are audible.
Okay. Okay. So going back, so we are looking. So a simple reaction between these two gives you a delta H, or the heat of reaction as minus 800, somewhere around the minus 800 kilojoule per mole. So that's a high amount of energy. So what we are trying to do, you are trying to extract the delta H or that energy and utilize it for various purposes. So that is why natural gas is also very enticing. And if you look at it, so what the natural gas extraction process typically has, so it has a lot of sulfur carbon dioxide that is present, so that needs to be removed. So it's a as you extract it, as you drill natural gas from the earth's crust, it's not something that you can directly use it as is. So that's one of the biggest problems. So you need to be able to refine it through several stages to kind of get to a final pure product. So you have sulfur carbon dioxide removal, you have water that needs to be removed, okay, and then oil and some condensate or waste materials that are there that needs to be removed. And then one byproduct that is very important and very interesting. So this is the natural gas liquids. This is nothing but things like propane, butane again. So butane and others that are extracted, okay, etc. So those that need to be removed also, because they are very highly valued products, so you can use them somewhere else for energy extraction. And then what you are then finally left with is pure natural gas, or CH4, that can be utilized or that can be burned to get very high energy. Okay, so why natural gas? So one of the main reasons why people are looking at natural gas is because it produces less carbon dioxide than coal-based energy generation. Okay, so the coal-based, if you compare coal-based energy generation versus the natural gas-based energy generation, so the CO2 production is almost half, or less than half, slightly less than half when you're looking at natural gas. So the amount of CO2 that you are generating goes down. So that is one reason why all the countries are now looking at natural gas based systems. So then the simple question could be like, what is the big deal? I mean, why did not somebody look at it? If it was so efficient, why did not somebody pay more attention? Let's say 50 years ago, instead of coal, why didn't we start using natural gas at a much earlier period? So the reason being, natural gas is so one of the challenges with natural gas is that natural gas is 80 times more heat retention, has more heat retention than CO2. So if you compare CO2 and methane is 80 times more detrimental towards what you call greenhouse gas emissions. All right, so that is one of the reasons why methane was not touched upon in the last 50-100 years. But now there are more technologies, more efficient ways of methane extraction, where the leakages are very low, and hence, the methane leakage to the environment is not as much as it was 50 years ago, 30 years ago. So people are able to contain methane in a much better manner now. So what we are trying to do now is being able to use it without much of it leaking to the environment. So that's where there's a lot of technology improvement in the last 20 years, and that's why more and more companies are moving towards natural gas based energy generation. So if you look at India, our own oil companies like ONGC, HPCL, BPCL, all of them are looking at more natural gas extraction and their usage in terms of production of power. Okay, so moving ahead, so the nuclear energy. why are we interested? I mean, why did I bring it up? Because now India has or produces about 6,000 megawatts of power from nuclear power plants. So we have about 6 power plants spread over about 3 states. I think two to three of them in Tamil Nadu, some I think, and then one Maharashtra, one in Rajasthan or so. So and this has picked up in the last 5-6 years. I think production of power or production of energy utilizing the nuclear. Okay, and so and then it is going on. So I think there is a roadmap or a road plan by the government to kind of double, triple it in the next 5-10 years. So even in the nuclear side of it. So one of the main reasons is that it is highly efficient. I'll show you in a few slides what I mean by that. And its energy density is very high. The amount of energy per kg of uranium is significantly higher than any of the other sources. So that is something I'll show you in the next slide. So in a typically what happens in a fission reaction is that you have uranium and then you bombard it with one neutron. You have barium and krypton that come out of it, and then it also produces 2 neutrons. So that's the good part, and these neutrons can now go attack these other uranium molecules. So it's a self-sustaining reaction, and the challenge here is that if you don't control it well enough, then it can be like a bomb, right? So that is the biggest challenge there. So you need to have a reactor where you have very precise control. Even though it is self-sustaining, you need a precise control on that to kind of maintain it at that level without going into a detonation kind of a phenomena. Okay, so then even the nuclear cycle is not as simple. You cannot take uranium, put it inside a reactor and say it will produce power. There's a lot of things that go in there. You have to do mining for uranium first. That's a big hassle, and that's a big environmental issue. So yes, I think nuclear energy has significant challenges in pertinence to the environment. But time and again, some of the countries have proved that if you do it with extremely good control, you can still be okay. For example, Japan had a significant source of nuclear energy. France did it for a long time without any accidents. But now they are trying to also move towards renewables because they are more safer. But I think when there was not as much renewables, France, Japan, Russia, and some of these countries have done a lot of nuclear plants, constructed them to generate energy. And I think Russia, we had one or two major accidents, but I think France and Japan typically haven't have any man-made accidents happen in their existence on the nuclear front. So I think yes, there is environmental concern, but it is a good source of energy if it can be harnessed well enough. If you dispose of the waste in the right manner, it can still function well. That's the whole idea. Okay. And when you talk about energy storage systems, I think one of the things you refer to is primary sources of energy and secondary sources of energy. So what do you mean by primary sources is typically things like what I've referred to so far: crude oil, coal, natural gas, nuclear, waste-based, solar, hydro, whatnot. And then the secondary energy systems are when you convert them into usable products, something like petrol, something like electricity, something like heat, something like a biofuel. So what I want to convey here is that the primary sources of energy are can never be utilized by themselves. So the primary sources always have to be processed in some manner or the other to get to the secondary source of energy, which are the ones that you primarily want to use. Excuse me, there is a lot of disturbance. Can somebody mute it?
I think it is.
Hello, can
We have muted all the participants.
yes?
Okay, now it is fine. Yeah.
Ah, okay. All right. So okay, so the primary and secondary sources. So I think the secondary sources of energy are the ones that are directly usable by you. So there is some transformation that has to happen when you talk about primary sources of energy to go to the secondary sources like petroleum, heat, and electricity, etc., etc. Okay, so I'll bring up this slide to show you where we stand and why, in a way, why fossil fuels are very interesting, are still very interesting, is because if you look at the energy density represented as million joules per kg. Okay, so if you look at this energy density million joules per kg, wood is about 10, one of the lowest among these. But if you look at the other set, which is coal, crude oil, natural gas, your LPG, whatever, whatnot. So all of them are in the 30 to 50 range. So that's very good. And if you look at uranium, that's significantly higher. So if you look at uranium, so it's about 80 into 10 power 6. So I mean, that's the scale of energy that uranium contains before that molecule becomes useless. That's the whole idea. So that's why the energy scale is significantly higher, 10 power 6. And if you look at a lot of these energy storage systems that are man-made, so they're significantly less than 1. So I think if you put it in this perspective, I think they're significantly lower. So we have a long way to go to or achieve the densities that are shown by natural systems. So that's where we stand, and that's why all this research in energy, is happening, so that we can try and catch up with the fossil fuels or the natural sources of energy. And just to give you a perspective, so I think if you have a 100-watt light bulb and if you use 1 kg of these materials, how many days that the light bulb run? So wood is about 1 day, the others are somewhere in the 4 to 8 days range. Whereas using uranium, you can run it for thousands, at least 1,000 years, if not more. And if you look at man-made, generally much less. So I used one as the 1 million joule as the reference, but I think if you see, it is much significantly lower than that, is the idea. So that is where we stand in energy storage. That is where we have to contribute, we have to work more, we have to understand more to kind of get to those levels. So this is 2019, generally the global energy consumption and where things stand today. So if you look at biomass, it kind of achieved saturation, and I think not much change in it is happening. Coal has been increasing. If you look at oil as one source, it's been increasing. Gas. So gas is one thing that has been, so if you see the increase, it has been rapidly increasing, let's say in the last 20 years. So there's a big increase happening here also in the usage of gas as well. And then if you look at renewables, this is a much smaller part. So that is where we are as a world in terms of the usage of different things, and renewables is still only contributes significantly lower, less than, I think it amounts to less than 15% of contribution or usage for the production of energy, whereas coal, oil and gas or natural gas are the primary sources. So like I said, I think it has one of the main reasons of fossil fuels is it has high energy density, significantly higher energy density. And we know the technology very well, so it's very hard to move away from them, right? So over the last couple of 100 years, we have understood very well on fossil fuels. So we say how to extract it is very well known, how to purify it is very well known. So it's a very established technology. So it's not very easy to move away from an established technology. That's one of the challenges that we will have when you want to move away from the naturally occurring fossil fuels to some of the other man-made or the relevant new energy technologies. So that's one of the obstacles that will be there. In a way, that has to be overcome if the government provides a lot of incentives. For example, if you're setting up a solar cell at your home, it might be much more expensive to set up the solar cell than getting power from the regular grid. But if there is a subsidy on that, I think you are more you'll be more inclined to set it up. So maybe 50% subsidy, and then some of the cost can be reduced. So in that context, like I said, established technologies are generally more cheaper because they're more established. So newer technologies are a little more expensive. We need to understand them more. So in that context, I think some of the help from the government has to come to kind of promote these. And that is what we have seen happening in the last 10 years or so. Okay. And the other one of the other interesting things about coal, oil, or any of these is they are very safe for any kind of transportation. So you move coal from Australia to India, nothing happens. You move oil from Australia to India or a far location, let's say not Australia, but rather we say Saudi Arabia to India, it comes in ships. It's rather very safe. So the materials themselves, the primary sources of energy themselves are very safe for transportation and movement. Whereas some of the man-made energy storage systems like batteries, we have seen that there are cases of safety issues. So that is another challenge that we need to address to be able to make something, more widely used. Okay, but what are the, so I think until now I've been articulating why fossil fuels are so interesting, or why fossil fuels look like they hold the major share in the world. Um, right, and then it all looks like until now all my explanation looks like they are very good. No, they are not. There are big challenges that are there with them, so that is what I'm going to discuss in this part. So one, people believe they will exist somewhere between 100 to 300 years. I think whatever the reserves that we have found till now in the Earth's crust typically are, I think, will last for 100 to 300 years, the crude oil or the natural gas or coal. So the context now is what after 300 years. Maybe we'll find new reserves, but we don't know. So what shall we do if there is no more of coal that exists or natural gas or crude oil that exists in 300 years? So that's one of the thoughts. That's one of the reasons why we want to go to alternative energy technologies. And so the second reason, so I think there's a lot of talk about global warming that you see that is happening in the last 200-300 years. I think it has been happening for a couple of 100 years, the global warming, but it is more predominant in the last 50 years because of the growth of technology. There's a significant increase in the technology, right? I think right from 19 or let's say 1990 or 2000s to 2020, 20-30 years span, you see a lot of, phone market has evolved, TV market has evolved, a lot of technology has come about, laptops, computers have evolved. So there's a significant growth in technology in the last 20-30 years, which leads to high energy consumption. And when that energy consumption happens from fossil fuels, I think there is a predominant effect on the temperature of the earth. Okay, so if you look at this graph, so what you can see, this is year zero is I think AD. They started at AD and they were looking at the concentration of carbon dioxide, methane, and nitrous oxide in the atmosphere. So what you can see is from 1800, this is typically when the industrial revolution started. You can see a significant rise in the content. So the CO2 content is increasing, the methane and nitrous oxides. It has been increasing. These 200 years, there is an increase, and then after 2000, you can see a exponential growth, right? There's an exponential increase. So that is what we are worried about. That is what we are looking at and trying to reduce, essentially. So all three, so carbon dioxide, methane, them both are carbon or greenhouse gases. So what do you mean by greenhouse gases? They retain a lot of heat within the Earth's atmosphere. So essentially your temperatures on Earth go up. So if you look at the last century or last couple of centuries, we had a temperature rise of about, I think 1.5 degrees centigrade or so. But the next century, this 2000 to 2100, the expected temperature rise is about 2 to 6 degrees centigrade, as shown here. And then if you look at this, in the last 5,000 years, the Earth only underwent a change of 5 degrees centigrade in the temperature. But then in the next 100 years, that same temperature rise will be happening if we go on predominantly using fossil fuels. So I think that is one of the main reasons why we need to be very proactive and try to use other technologies where that can be curtailed. You might ask, I mean, what does 1 degree centigrade change? What does 1 degree centigrade do? I think if you look at your body, for example, as a very simple example, so you can say that, 98 goes to 100, you have a fever, right? That means a stark difference in how your body functions. So it's the same anywhere else. So I think a degree temperature in rise will typically lead to a lot of polar caps melting and things of that nature. So it will have a profound effect on the life on Earth. Okay, so main causes, like I said, CO2, CH4, particularly CH4. I told you, or I referred to it when we talked about natural gas. CH4 is 80 times, stores 80 times more heat than CO2. So that's a bigger problem in global warming. But then if you can efficiently use natural gas without any leaks, yes, you can curtail that problem, or you can overcome that problem essentially. Okay. I showed you this power plant, coal-fired power plant before. So everything looked very nice, right? Everything looked very good. So I mean, why do we have to move away from coal? But the overall efficiency, there's a lot of mechanical parts involved in coal or electricity generation using coal. There's a lot of mechanical components involved. So because of the same, the efficiencies of the new technologies, I think the best technologies that exist today have efficiency slightly over 50%. 50, 55, but they are more expensive and so on and so forth. The general efficiencies of these coal plants are only 40%. And if you look at old plants, like we have in India, several plants have been around for about 40, 50 years. Those give only efficiencies on the scale of 30%. So what does that mean? The whatever 40 million joules per kg of energy that a coal has, you're only able to extract 12 out of it, right? Essentially. So from the 40 million joules, you're only extracting 12 million joules. So you're losing out on the 28 million joules of energy. So that's one of the problems with fossil fuel based technologies. Most of them have to undergo some processing, and when they undergo the processing, the efficiencies go down. So essentially what you are extracting will be comparatively much less than what you can extract. So that's one of the challenges. So the efficiency of these is low. So if we try and move, I know the efficiencies of some of the renewable energy sources is also low, but you can, enough exploration has not been done in those areas to kind of say if it is comparable to this or better. So I think with more effort, more energy, more technology development in those areas, we might see efficiencies go up and up and up. So that's one of the main advantages in trying to go into renewable energy sources. Okay. The other thing, so if you look at this graph here, so this is the typical load you see. If you look at a small community, this is the typical load that you see. So what do I mean by this? So I think this is where fossil fuels have a big problem. One of the biggest challenges of fossil fuels. So what is happening? So this is nighttime. This is until 6 in the morning, right? 6 in the morning. And this is somewhere, let's say 8, 9 in the night, or 8 o'clock, and this is 10 o'clock in the night. So what happens is that your energy consumption drastically varies when you look at a single day. If you look at a particular day from 12 o'clock in the morning to 12 in the night, what you end up seeing is 12 to 6, you might not have much energy consumption. Everybody is sleeping, or most people are sleeping. So you don't see much energy consumption. But then you look at people going to offices, and then going to schools, whatever that needs to be done, going to shops, whatever. So there is a sharp rise in the energy requirement from, let's say, 6 to 8 or so. So in 2 hours gap, you have a sharp rise in the energy requirement, and then it more or less stays there for the next 4 to 6 hours of the day. So that energy, and then there is a small peak in the evening. Typically when people come back home, they switch on the TVs, and they do whatever work is at home. So there is a slight increase in the energy requirement, and then it goes back down by the night time. So what is the challenge? So when you want to, so what has to happen if you are using a fossil fuel based technology? What has to happen? So you need to keep generating energy at this level, at the maximum level, right? So in order to cope up with this energy at this peak, you have to generate energy always at this 23,000 megawatts level. So what is happening? A lot of it is going waste if you're not using it in these timings, right? So a lot of this is essentially going waste, but you have to produce it because you require it at some point of time in the day. Why? The reason being that fossil fuels, you cannot generate it. So you cannot call the coal production company and say within an hour I want this kind of load increase. It cannot happen. Those are all mechanical components. They require significantly more time So this is where you say the response time of the energy generation system or energy source system. So the response time of fossil fuel based industries is significantly higher on the extent of hours to days. So it cannot be a millisecond or seconds to minutes response time. That happens in your batteries. For example, if you hook up a battery, you see an immediate discharge of energy, right? So it is in the second scale. Whereas when you're talking about fossil fuels, typically energy generation happens on the scale of hours or days. It takes that much time for energy generation to happen. So that's the challenge. So huge variation in energy demand at different time of the day. So it's very hard to generate that energy. Okay, so what, like I said, you have to do it at very high peak to be able to cater it. Or else what you do 20 years ago or until 10 years ago or so, what India used to do, you used to see power cuts, right? So what you do, you generate the energy at some point, at some lower location. And in the peak demand time, you cut energy to one community and give energy to another community. So essentially, that's why we had power cuts, significant power cuts maybe 10, 20 years ago, when, we were not able to produce so much. So what you do, you give it to one community at one point of time, cut the other, so on and so forth. You can have those timings. But what can energy storage systems do? And lot of the power plants, not only the power plants, the subdivisions where the power distribution happens have these energy storage systems. So what does that do? So when you can generate it at a much lower level at 20,000 megawatts. So when you're not using it, you can charge your energy storage system. So you are charging it during the night time until early morning time and so on and so forth. You are able to charge it using that extra energy that is there. And during the daytime, you don't have to now rely on the on your power generation plant, but rather you can use your energy storage system to kind of discharge. You call it, what it is doing is discharge. So it is essentially giving you the required energy. So now you can see how the problem of high generation has been brought down when you have a energy storage system along with your power generation source. So there are different technologies that are available now that are being used at the substation level to essentially kind of supplement the extra needs of energy this way. So that is where energy storage system plays a significant role, even for fossil fuels. So that is why I think without storage, the energy generation and distribution is very inefficient. So the take-home message would be that energy storage has to be hand in hand with any energy generation source for it to be highly efficient, or else you can still do it, but a much more inefficient way. And one of the other important uses, I think, other important changes that you see. So if you look at any coal-based energy generation or any of the mechanical component energy generation, there is a lot of variation that can happen in terms of, voltage generation. So this is significantly, I think voltage fluctuations are very high. So, but when you use a battery that comes along with that, I think when you run through a battery, what happens is that these fluctuations go down, and what you see is a much less fluctuated line. So essentially, if you connect your energy generation source with a battery and your voltage comes through the battery kind of absorbs all these modulations or these undulations, and essentially what you get out is a much lower fluctuation in voltage. So that's why if you had paid attention, if you had looked at your own house, inverters, typically all the current runs through your inverter battery. The reason being it can accommodate all the voltage fluctuations, and what you get out into the house is typically something that's less fluctuating. So what does that do? That will keep your appliances or electrical appliances for a much longer period of time, or that will make their life longer. Otherwise, if you see a lot of voltage fluctuations, the appliances might get burnt and all these problems come in. Okay, so that is so those are the couple of things that are very interesting where energy storage systems quite help. I mean, they're used now, and I think they'll be used as long as the energy sources exist. And the other problem, I think Professor Pillai was referring to, environmental problems, or, the air being not clean in India or clean enough in India. Where does that come from? So it is primarily because of what you call SOx and NOx emissions, the sulfur oxides and nitrous oxide emissions. So where do they come from? Sulfur oxide comes from fuel that contains sulfur. For example, petrol is relatively much more pure, so it doesn't contain any sulfur, whereas diesel-based operations, diesel has some amount of sulfur. So what does it lead to? I think leads to sulfur emissions, sulfur oxide emissions. Okay. And nitrous oxide emissions. So when you are utilizing petrol or diesel, typically you have to heat it to 900 degrees centigrade, right? So in your, if you look at your car, if you take your car, the temperatures at which the combustion happens is about 900 degrees centigrade, and then you see that air is used as the gas for combustion, right? So in air you also see nitrogen. So what happens is essentially at that temperature it's very hard to prevent formation of nitrous oxides or NOx kind of substances. So there is something called a platinum. If you have heard of it, if you have known, I think there's something called a catalytic converter which prevents this from happening. I think it reduces the amount of nitrous oxides formed, but every car does not have a platinum converter. I think those catalytic converters are expensive and you only see them in higher end cars. So I think the problem of nitrous oxide emissions and sulfur oxide emissions is still there in India. So what does it do? So these emissions essentially start forming small particles in the air. They react with various things in the air and start to form small particles, which you call as particulate matter. And why is it so concerning, the particulate matter? So this is just to give you an idea. So your hair size is just so the hair size typically is about 10 microns in diameter. The fine sand on the beach is about 90 microns in diameter, and so on and so forth. So whereas the particles that I am talking about, the particulate matter particles, are less than 2.5 microns. Okay. So what is the problem? So I think your simple question might be that, why are we concerned about it? I mean, it can still exist, but what is the concern? So the problem is this particulate matter, it can go inside your lungs, but it cannot be pushed out. The reason is that your lung does not have enough pressure to push it out. So when you inhale it, these particles go into your lung, sit in your lung and stay there forever. So when you exhale air, the lung does not have that kind of pushing power, or what you call pressure. Simple terms, it cannot have that enough pressure to push these small particles out, because they're so light they settle in your lungs. So what does that do? That reduces your breathing capacity with time. If you're continuously exposed to it day in, day out, so I think over a period of time, you lose your lung capacity, and that is a realistic problem that needs to be addressed. And that's one of the main reasons why I think there are so many new policies in the last 10 years that are trying to reduce these particulate matter emissions. So we look at Delhi every year, right? When winter time comes, you look at Delhi and say, its air quality is very low. So it is a variety of reasons. Vehicles, one, burning of wood. So that is, I don't know how many of you have read this. So there is a GO that came out maybe 6 years ago, which says you cannot burn wood or leaf anywhere in a public setting. So if you're burning a leaf or a wood material or a leftover tree material, you cannot burn them. I think you rather need to take them, put it inside the soil and compost them. There's a law, but that is not followed as much. But there is a law that says you cannot do that. There's a fine for it, 5,000 rupee fine for doing that as well. The reason being, you start burning, any of the plant-based waste, you generate the particulate matter again. So that's the problem. So if you are burning it, it slowly generates particulate matter, and that particulate matter, like I said, has big concerns. So this is a study, I think, done 4 or 5 years ago, I think from 2016 or so. I haven't seen any other study after that, something like this. What they have done is they have tested children and their lung capacity, children below 15 years of age, and they are age group 10 to 15 years, and they have checked their lung capacity. So what they have seen is that several children, I think up to 40% children lose their lung capacity in big cities like Delhi, Mumbai, Bangalore, and Kolkata, primarily because of particulate matter. That is something very significant, very not very good for the society. So I think this is a major challenge why we want to move away from fuels like petrol, diesel, both in an industrial setting as well as a vehicular setting. So if you want to stop particulate matter, we need to. That's why if you look at a new vehicle disposal policy, there's I think last year or this year, there's a new policy which gives you some money to dispose of your old vehicle. Why are they doing it? The simple reason is that a 20-year-old, 30-year-old vehicle will emit a lot more particulate matter than something that is only 2-3 years old. So the government is now trying to force these old vehicles to come off the road to prevent this particulate matter pollution. So it's a very important thing that I think there are some steps taken in that direction to prevent particulate matter as much as possible, and I think it is imperative for us to follow to kind of get it down. Okay, and apart from this, these are very general. Whatever I talked about so far will apply to a lot of countries as well, or the entire world. This slide will present what is very particular to India or very peculiar to India. Few things. One, our rural areas are quite segregated in comparison to many places. We don't have, I think some of the connectivity between rural and urban areas is still a challenge. So how do we go about it? How do we have power lines to that kind of remote areas? So that's a challenge. So rather, the idea here is that instead of a fossil fuel, why don't we set up a solar energy generation plant in a small village that is off grid? So you can set up a plant there, and that can take care of all the needs of that small village. If it's only like 100 families staying there, it can take care of the village. So in that context, any renewable energy source and generation will be generation and storage will be very efficient. So one of the reasons being the connectivity. And if you look at urbanization, for example, look at Hyderabad. In the last 10 years, I think I'm from Hyderabad. So in the last 10 years, there's a drastic change in the number of people coming to Hyderabad and wanting to stay here. So what happens is that there's a rapid urbanization or growth of apartments, growth of commercial buildings and things like that. So where do you get the energy from? It's not as simple to raise the energy of coal-based generation systems, right? You have to build a plant to kind of improve that output. So that will take years together. So one of the ways to do it is, let's say, if you go to solar energy type of thing, wind energy generation, any of these renewable energy sources, it's much easier to extract energy from them, easier to set up, takes much less time to set up and extract energy. And they will also play a significant role when you're talking about urbanization. So for example, imagine a society will have its own solar plant or solar cell setup where it doesn't have to get any energy from the grid. So that's the way to go. I think that's the way to go for urbanization. You don't have to depend upon anybody else for getting your energy. You rather have your own, you have your own solar energy setup and you can get the energy required. So those, some of those things I think are very particular to India, peculiar to India. So I think comparison to some Western countries like Europe and US, I think we need to take this up on a much bigger scale, much bigger war footing scale to kind of overcome these shortages. Okay, and so if you look at the power generation in India, so I just wanted to give you a picture of the power generation in India. So this is thermal. So thermal is still consists of coal, lignite, natural gas, diesel based and whatnot. So it's about 61% or 61.5%. One of the good things that happened in the last 10 years is renewables. So it is primarily wind and solar. That is what we have primarily in India, wind and solar, and that accounts to 25% today. As it stands today, this is March 31st, 2021 data that I got from the NIC website. So it says that 25% of our energy comes from renewables today, and that's a good achievement considering this whole thing came up in only about 10 years. I think until 2008, 9, 10, we didn't have much in the renewable sector. I think very little. I think it only grew in the last 10 years. So I think as a country, we are heading in the right direction. That it gives me a lot of positive positive vibe that we are going towards the right direction. So 25% using renewables, and then there is hydro based is 12%, and then about 2% of nuclear. Nuclear also has picked up significantly, I would say. So in the last 10-20 years, I think. So we are all moving in the right direction, but we have to do more. I think renewable energy, if we can get to like 50-60% share of renewable energy in the market, I think that's the ultimate thing that you can do. Reduce the dependency on the fossil fuels. Rather, it should be all renewable. Okay. And among the renewable, like I said, so I think if you look at coal is the primary one. So 80 into 60 is about 50% comes from coal. Overall 50, I think it is 51% or something comes from coal. Others are lower. So we are still, as a country, we are still dependent on coal for 50% of our energy generation. And if you look at this previous slide, some of the charts, so like I told you initially, right, our coal is a low grade coal. It's not a high grade coal. So our energy, so we cannot, I think several of the coal deposits cannot be utilized in power generation. So we have to buy it from elsewhere. Like primarily now it's Australia is one of the sources, or Australia supplies us a lot of coal. So what happens is you are also dependent on another country for your energy generation needs. That's not a very suitable scenario. What if tomorrow they stop giving you coal? I mean, it won't happen, but I'm just talking about a hypothetical case where these things might happen. So you need to be prepared in that case. So that's one of the reasons, renewable energy sources are important, because that will reduce our dependability on any other country or any other source. Essentially, we as a country can be self-sustainable when you go to renewable energy sources. Okay, so I think enough said about fossil fuels. So I hope I've given you enough reasons why we should be looking at energy, renewables and energy storage systems. So this is a prelude on why fossil fuels are good, have been good so far, and still are probably good in terms of efficiency and energy density. But what are the challenges that have started cropping up in the last 20 years, and what are the more significant challenges that might come in the next 20-30 years? So I hope that whole overview gave you a good understanding on those concepts. And then so we'll move to renewable energy. So like I said, so one of the main things whenever we talk about green, whenever we talk about producing our own things, sustainability is very important. Sustainability is very important in everything that we do, in my opinion. So it has to be sustainable, right? If you're doing something, it has to be there for the next 100 years or 200 years or 300 years. You cannot do something just for a day and say, okay, we have accomplished something. No, something has to be sustainable for it to be efficient day in, day out. And then other benefits are something very well known: low pollution, low maintenance, and all these things. Good economic benefits, we have discussed enough. Then what is the challenge? So why haven't we moved to renewable energy sources like 30 years ago? Why haven't people moved to it? Even today, I think we find it quite challenging, right? In terms of, if you look at renewable energy systems and being able to implement them, you still think it's challenging. Why? So I think one of the points that was repeatedly mentioned by Professor Pillai, reliability of supply. So wind and sunshine are highly intermittent. So the weather dictates the supply. So that is one challenge that we encounter, especially India. For example, India is much better in terms of sun availability, but a lot of the northern hemisphere countries are not so. So I'll show you in the next slides what I mean by that. And the efficiencies are low. So I talked about this, because we are still in the research stages, we are still understanding these systems. Our effort into these systems has only started in the last 2 decades or 20 years. So it has still, we had done, I think we have achieved a lot in the last 20-25 years in this renewable energy domain. But I think there's a long way to go to understand them further. And this high capital cost, I think I mentioned it before, it's very expensive. Initially, it's very expensive, so it has to be subsidized by the government, or some form of help has to be there for people to. So this is all more to do with economics. I mean, when something is available for 1 rupee, why would you buy something for 5 rupees, right? So that's a good question. Some can do it as a philanthropy, but everybody cannot afford it. So it's some form of that negation, or some subsidized thing has to come initially, and after it picks up, the cost will go down. So it is very natural. So for example, solar cells, when it started in Germany in the early 2000, I think their kilowatt hour cost was something close to 10 euros or something. And by 2010, it dropped to less than €1 per kilowatt hour of generation. So as you increase the scale, so this is what you call the scale of economics. As you increase the scale, the cost goes down naturally. But that increase in the scale has to happen with some kind of support in the beginning. That's where it is very important for countries to support it. And so solar energy, I won't do much. I think we have a whole lot here. So the only thing I wanted to show here. So for example, if you look at 3 different places, Cairo, you look at London is the blue one, Cairo is, red one, and Kampala in Africa is the green one. So if you look at Kampala, so you can see that if you look at the solar radiation in a year, so it from 1st Jan to 31st December, you can see that the variation is not much when you're talking about Kampala. So it's fine. So you're not much worried. But as you go to Cairo to London, you see that there's a huge variation in how much sun, the incident sunlight happens, on those places. So that's where the challenge comes in. So I think this is where it is not as straightforward to use solar energy at any location. So what is happening, or what is the best way to go about this, is again use a energy storage system, right? So what you do in the night time, again charge, or in the daytime when you have a lot of sun, you charge your energy storage system. Nighttime you can use it, or when you have sun, you charge it. When you don't have the sun, you use it. Things like that. And then wind energy, the second one. So if you look at the wind energy, it has gone substantially. It has grown substantially in the last 2-3 years worldwide. So this is worldwide. You see that it was kind of in the 300, 400. But now it reached about 650, 740. And you see the growth is significant, especially in the last 2 years. And I think all the countries are very much invested in wind energy and are trying to go that route. And this has been existing for a long time. We have had these kind of mills there from 7th century. So people knew this concept. Only now I think we are putting it or implementing it, the technology, or implementing the technology at a much larger scale. Okay. But again, it's the same problem with wind, just like you saw it for sun. Wind is intermittent also. So if you look at the whole, this is a 6-month, or so if you look at this, I think this is a year-long thing. You can see the ups and downs, right? Same thing. If you blow up for 1 month, you can see the ups and downs. So there's a significant change in how wind blows, and the wind direction, all those things play a very significant role and very important role. So wind is also quite intermittent. So what do you need? Again, you need an energy storage system. So this is where energy storage systems, like I said, are very important for any energy generation source. So you can have a very highly efficient solar cell, highly efficient windmill, but without an energy storage source, night times you cannot use solar energy. When there is no wind, you cannot use wind energy. So a storage system has to be, so there's no separation of these two. So whenever you talk about energy generation sources, you need to think of it as there is a storage system with it. Without a storage system, the efficiencies are very, very low. Okay, so same thing. And so this is the sun plus wind combined. So for example, I'm just showing both, and different times of the year, you can see the variation. Just something very similar to what I've shown in the last 2 slides. There is a huge variation in the energy per day. This is exajoules per day. That's the variation. So how do you overcome the variation when it goes very low? Is I have an energy storage system. That's as simple as that. Okay, so that is about wind and solar. Biofuel is another interesting thing. So I think we are not going, I think at least this program is not going to cover a lot about biofuels, but I just wanted to touch upon the topic so that if somebody is interested or in that area. So biofuel primarily one of the main reasons is why biofuel is very interesting, or ethanol based. So I don't know if anybody has looked at the news in the last week or 10 days. So the government now is trying to put about 20% ethanol in your petrol as an additive. So it was I think it was 10% until very recently. Now we are trying to move our engine. So I think there is testing happening to see if the regular petrol engine can sustain 20% ethanol. If they cannot, what has to be done to kind of have 20% ethanol blend. So it's a blend you have 80% petrol and 20% ethanol, which is like 90-10 now or so, around that range. Government is pushing for 80-20. So why ethanol? Ethanol, one of the advantages of ethanol is, if you look at it, if you want 1 million BTU of gasoline, in the second figure, I'm trying to circle it. So it says 1 million BTU of gasoline, in the sense petrol, at your fueling station. The amount of energy you utilize to produce 1 million is 1.23 million. So when you say amount of energy, it includes drilling. For example, you're drilling it into the earth's crust, you spend energy there, right? And then you have to extract it, process it, all that consumes energy. So if you actually look at it, we are at an energy loss. So you are using 1.23 million BTU of energy to produce 1 million BTU of gasoline. Whereas if you look at ethanol, in order to produce 1 million BTU of ethanol, you essentially use only 0.78 million BTU of energy, or fossil energy. That is mainly goes into processing various things. The main savior, why is it the case? The main savior is because sun energy is utilized by the plants to produce that. So I think we don't count this, right? So this is happening on its own. So there is some energy that is used up here, but that comes from the sun. So essentially, when you look at ethanol as a fuel for your industries, as a fuel for your car, you are looking at a net. This is net negative. Whereas petrol and others are net positive. So that's where ethanol comes in. That's where ethanol is very enticing, and people are still looking at ethanol as one of the sources of energy. And the second good thing with ethanol is that carbon cycle. So we have talked about, I think Professor Pillai touched upon, carbon dioxide generations, the carbon cycles, right, is in a bigger context. So if you look at the carbon cycle, if you look at fossil fuels, it's a very long-term unbalanced cycle, right? So you are burning fuel now, you're generating CO2 now, but the same CO2 has to be captured in something and put inside the earth, which will take 1 million years to regenerate to fuel. So essentially, the carbon dioxide you're producing today will only be regenerated after, let's say, 1 million years. Right, so that is what you say, a long-term unbalanced cycle. So this is what is written here. So long-term unbalanced cycle. Whereas if you're using ethanol, it's a short-term balanced cycle. Why? You're generating CO2. Let's say you're using a liter of ethanol, and equivalent to that, you are planting trees or you're raising corn. Wherever you extract, you can generate ethanol from sugars like sugar cane. You can generate ethanol from corn, etc., rice, everything. So if you are using a liter of fuel today, but if you are planting the same amount of trees somewhere to grow more ethanol, so whatever CO2 you are generating today will be utilized today. So essentially what you call a much balanced cycle and short-term cycle. So that carbon dioxide essentially you're producing in your car using ethanol will be utilized by the plants that are producing ethanol. So that's one of the main advantages of ethanol. So if you look at ethanol, if we can make it a reality, yes, it is truly very interesting and it is one of the technologies that will reduce the overall net, it will increase the net positivity of energy as well as reduce the carbon dioxide. But then this is a big question. I think this is a very debatable question that you have food or fuel. So I think this it's very hard to say. So if you say there's not enough food for people to eat in countries like Africa, and if you say I want to produce fuel, what is important? So I think this is a big question that has been there for a long time. When you talk about ethanol, so I think we need to find a way around it. In the sense, we need to be able to feed everybody and then go this route. But if not, then I think this is always a question that will be there. Okay, and just to put it in perspective, I've listed. So the left hand side is all different types of renewable energy sources, and this is annual energy rates like 23,000 terawatts, hydrothermal 3-4 terawatts. All this is annually. And then the coal, uranium, these deposits, if you see, this is the total reserves that we have essentially. So if you look our world energy consumption, I think this is 10 years ago. I don't have a better data. I think this has probably grown to about 20, I would think. But nevertheless, if you see the solar itself, even with 1% efficiency, you still get to 30 terawatts, right? If you're able to tap all that solar energy. So we are still significantly higher than what the world energy consumption today is, 10 times higher. So that's why solar is so interesting. That's why we are going to be talking about solar for the next 2 days, and then we'll talk about how to efficiently use solar by doing energy storage. That's the whole premise of this, I think, workshop for the next 4 days. And this is something I like to show a lot of people. See, what is the ultimate goal that we want to achieve by going this route? So imagine this concept where you have a house and you cover your house with solar panels, completely with solar panels, or something called solar paint. These days, I think there is an idea about something like a paint that you can use that can absorb sunlight or solar energy. So you actually can paint it or whatever, however you want to do. But imagine you have solar panels which can produce hydrogen, which can split water into hydrogen, oxygen. You can produce hydrogen. You can produce electricity also. So imagine you are giving back to the grid. You have excess energy production at home, so you are giving some of it back to the grid. So you can use the solar heating panels for water heating and other purposes also. And then you can use hydrogen or electricity depending on what kind of a car you have. I put hydrogen here for fuel cell, talking about a fuel cell car, but if you have an electricity directly. So what does this show? In the picture is trying to show the self-sustainability. So essentially you don't depend on anything for your power needs, but rather when there is excess energy, you are able to donate it to the grid and you are able to take care of all your energy needs, essentially something like that. So this is what we are aiming for, I think, as a world. I think we are trying to aim towards this self-sustainability of individual people or individual houses as well. Okay, so what is, like I said, what is energy storage? So energy storage is a good balance between supply and demand. That's as simple as that. I think in the simplest terms, I look at it as, the balance between supply and demand. So there is a high supply, you are storing it in energy storage system. High supply, low demand, you store it in an energy storage system. And there is high demand, low supply, you extract energy from an energy storage system. So it's, in a very simplistic sense, it's just a balance between supply and demand. So I think we discussed about several of these. I think, I think this slide is okay. So there are different types of energy storage systems that are available. Okay, so mechanical energy storage systems, you see, so there's pump storage, there's flywheel technology, there is compressed air technology. If you go to electrical, there is capacitors, thermal, molten salts, chillers, chemical, hydrogen usage, methane, natural gas we talked about, and electrochemical. So this conventional batteries, various types of batteries, let's say. So I'm going to go into a little bit of detail into some of these topics. I think just give you a very basic idea about what they mean, and so that if you are interested, you can get started in those areas. So the first one is compressed air energy storage. So what happens in this compressed air is that you take air, so this is at the bottom of this, you have a cavern or what you can call typically a big hole in the earth that is surrounded by different rocks. So what you do, you compress the air and put it inside, right? So when you have excess energy, for example, here they are showing that you have a PV farm, you have sunlight, you have excess energy. What you are doing, you are taking the energy from them, compressing your air and storing it here. And then there is a demand when the sunlight goes down. When there is a demand, what you can do, you can take the air up and use that air to kind of generate electricity. So you can use that compressed air to heat water, and the water generates steam. Steam can be utilized to generate electricity. So this is what you call compressed air energy storage. So this is, it's a low cost energy because you are not utilizing as much mechanical storage happens in the earth. As long as you can find a big area where you can store a lot of this compressed air, there's no challenge with it. So it is almost inexpensive, and then you are extracting it when it is needed. And air is a medium, air is the medium here, and then it's environmentally friendly, so you don't have to worry about it, right? You use air, compress it, put it inside, take it out, decompress it, extract energy, and then again it is left out. So you're not polluting air or doing anything there. So in one way, it is one of the most environmentally friendly techniques that you can think of. And I told you about fast response times. So that is very important when we are talking about energy storage system, because some responses have to be very fast, instantaneous, some can take time. So for example, compressed air energy storage system is a fast response system. So as soon as you recall air and produce energy, you can give it out. So that's one of the, so the challenge being underground storage is a big challenge. So you have to find the right space, essentially the right location to store all this. So I think usually what I think now it has not been explored as much as in the last 5 years. I think last 5 years people have explored compressed air also quite a bit, and now I think countries like US have several places where they do this compressed air energy storage. It's a very interesting system. It's a very straightforward system, only that you have to have the right location. So the location, typically what they do, they, wherever they dig the coal from or extract anything from the earth, they are using those locations to kind of put compressed air in it. But one of the things that needs to be understood is the geological pattern. So you need to understand the geology of that location to kind of be able to say whether we can utilize it or not. So that's something very important also to understand it. You cannot go to any location and put air. And if something were to happen, then it's a huge problem. So it has to have a very methodical approach to be able to implement it on a large scale. Okay, so that is about compressed air, and that is a very interesting and very interesting research topic. I think if somebody, if any of you is interested to take it up, I think that's not being explored as much as required in the present scenario, at least in India. So that's something people can look at. So the second one is flywheel energy storage. One of the mechanical energy storages is flywheel energy storage. So what you have is a rotating mass here. So essentially you use electricity, excess electricity, to convert it into kinetic energy, and you then extract energy from the, first you connect the electrical energy into kinetic energy, and then you can, whenever that is required, energy is required, you convert the kinetic energy back into electrical energy. That's what, in a simple terms, that's what you're doing in a flywheel energy storage. Okay, so kinetic energy is stored. There is a built-in rotor. It acts both ways, converts electrical to mechanical or kinetic energy here, and then back mechanical to electrical. Again, it has a very fast startup time or response time. So very interesting because of that. So if you have a flywheel, you can instantaneously generate energy if you want. The main challenge here is because everything is rotating all the time, continuously, sometimes at very high speeds, the materials are a big challenge. So what material to use? Because there will be a lot of stress on the materials because it is continuously rotating. So the materials can be damaged over a period of time. Like I say, if you're taking, if you're running it continuously, the material degeneration can happen. So when the material degeneration happens, the problem is the durability. So that is the main challenge in flywheel energy storage. Okay, so that's one of the energy storage. And then batteries. So I think Dr. Martha and myself are going to talk about batteries in detail on days 4 and 5. And we have Dr. Prateh Basak from ISCT will talk about electrolytes in batteries. So I think generally, I'll just give a very basic, input into what batteries mean. So there are two types, primary, secondary, as you all know. primary is use and throw type of batteries. So you use these batteries in your remotes, in your watches and things like that. So, and then secondary is the rechargeable battery. So you things like lead acid, lithium ion, and all those fall under that category. So I think I won't go into, I think we'll on days 3 and I think days 4 and 5 we'll go more into batteries. We'll discuss more about them. So the other interesting thing is capacitors. So if you look at capacitors, there are two main types, one electrolytic capacitors, one, supercapacitors. So what you have is, these are low farads, generally rated in picofarad to microfarad. These wet ones are microfarads, whereas supercapacitors are in farads. That's the main difference. And their usage is different. So these are used to filter signals and whatnot. These dry capacitors, you can see a lot of filtering, signal filtering is where you see them. Supercapacitors are more predominant in the energy storage domain area. Okay, more and more people, I think more people utilize supercapacitors when you're talking about energy storage. And when you talk about supercapacitors, you can now divide them into two types. One is double layer capacitors, one is supercapacitor, one is pseudo-capacitors. The double layer capacitors, there is no reaction that happens. Okay, no reaction. So what you see in a supercapacitor or a double layer capacitor is only charge migration happens. So if you take a material, on one side of that material, if you take a material like an electrolyte, you have a material here, solid material, let's say, and you have an electrolyte on the other side, right? So in this, you have charge accumulation. So one charge, like positive charge on one side, negative charge on one side. So that gives rise to the voltage, and essentially that's what you are doing. This is what you call a non-Faradaic type of double layer capacitor. Whereas you talk about pseudo capacitors, there are reactions happening. So the voltage difference and current and all come because of the reactions there. So that is the main difference between supercapacitors when you look at them. And if you want to compare a supercapacitor and a battery, so I think one of the questions could be, what is the difference between a supercapacitor and a battery, or a capacitor and a battery in general? So a simple analogy in there would be like, you are running a 100-meter race and you are running a marathon. For example, if you are running a 100-meter race, what do you want? You want high speed. You want to be extremely fast, and you want to finish as quickly as possible, right? So those are some of the things that you are looking for when you are running 100-meter race, like Usain Bolt, right? So that is what you are achieving in a supercapacitor or a capacitor. So it gives you very high energy in a very short period of time. So if you are looking at something like starting your car, what does it require? It requires very high energy for a fraction of a second to start your engine or ignite your engine. So supercapacitor will play a better role, or will give all that energy. Whereas battery is more like a marathon runner. So, what do you want in 10 kilometers, 20 kilometers run? You want a continuous energy source, right? You want to be able to discharge energy at a constant pace. Without high speed or low speed, right? So we want to maintain one speed and continuously discharge energy. So we want a lot of energy which will come out at a constant rate. Okay, so that is what is the difference when you're talking about a battery. So battery is high energy, generally low power discharge, whereas capacitors, low energy, high power discharge will happen. And just to compare, so like I said, so charge discharge happens in seconds. In supercapacitor, it is usually minutes in lithium-ion batteries. So that's the difference. So these cycle lives are much higher because they are very fast charge and discharge. Cycle lives higher. The cycle lives are generally lower. If you look at specific energy and specific power, so the specific energy here is low, whereas the specific energy here is much higher. Power is much higher here, comparatively much lower. So that is the difference there. So it says lithium battery has higher energy but gives out slowly or constantly, whereas supercapacitor has lower energy but you get a burst of power. So that is the difference, primary difference when you're talking about capacitors and batteries. And I think our talk would be incomplete without talking about hydrogen energy or hydrogen-based energy system. So I think this is something that people have looked. I think people have looked at hydrogen generation and use of hydrogen as an energy source maybe 20 years ago, and I think somehow after the batteries came into picture, I think after the lithium ion metal ion batteries came into picture, I think this aspect has not been studied as much. But then in the recent, I think. Few years, you can see that there is an increased interest in this area now. I think for various reasons. I think it gives you there are new materials that are there out there which can actually generate good amounts of hydrogen, and this reaction can happen in a much faster manner and things like that. So where can you use the hydrogen? When we talk about hydrogen economy, you can use directly for transport, actually in fuel cells. So you can use it in a fuel cells. You can also burn hydrogen directly in a tank and use it as your energy source in a car. That can also happen. Can also be used in fuel cell. You can generate electricity directly, and you can have a chemical way of so for example, you can use it also to for chemical reactions and be able to produce certain chemicals. So those are so hydrogen, essentially what I mean to say, can be used it in any application. That's the whole idea. That's why it is so relevant. So there are various ways you can produce hydrogen. So I'll list. So if you list them here, you can produce it from fossil fuels. Okay. So you might have uh, heard about steam methane reforming, right? So you can take the same methane that we talked about initially, right, as a natural gas, and then you heat it with steam. So what you end up getting is carbon monoxide and hydrogen. So you can actually, most of the generator hydrogen that is used is generated in this way now. So steam methane reforming. You can use biomass to generate hydrogen, do electrolysis of water, break water into hydrogen and oxygen. You can use thermonuclear ways of the same. Okay, there are various ways you can produce hydrogen. And so here I'm showing you how the water splitting. So essentially you are taking water and then water is being converted into both. One side it is oxygen, one side it is hydrogen. So there are various ways you can produce hydrogen. We have known enough. I think fossil fuel based way is the most widely accepted one now. So we are now trying into other areas, trying to split water using sunlight, trying to split water using a good catalyst, electrocatalyst, and things of that nature. But one of the main challenges is the storage itself. Okay, why hydrogen? Why do you want to? I mean, why do people even look at hydrogen? The other thing is hydrogen, it diffuses very fast, so fastest in air. So when there is a leak, for example, in hydrogen storage plants, it diffuses fast in the air, right? So it disperses fast. So the safety aspect is is reduced. So you don't have to worry about, because it is now very well dispersed. When it catches fire also, it won't be a big, I mean, there's a very less chance of catching a fire. That's the whole idea, because it has better diffusion, even if there is a leak. So low density, so it will rise faster than methane, or any, for that matter, it will easily rise up. So it won't stay in the lower levels, it will go up. So your safety aspect is increased because of that. And it is non-toxic. So one of the main reasons. And it can be ignited with lower energy in comparison to petrol or methane. And then hydrogen air temperature is lower than petrol air temperature. So that's if you are putting it in your car directly. So that's a big advantage. The flame temperatures you use for petrol and air is something like 900 degrees centigrade. It's much significantly lower than that. So then you can get rid of nitrous oxide gas emissions, right? So that is one of the. So there's a lot of advantages of nitrogen. I think if you want to use it as an energy source. The big challenge is the storage of nitrogen. So the existing technologies can store it as gas cylinders. Gas cylinders, you might have used it in the labs all the time. Those kind of small cylinders, or you can also store it in big cylinders using cryogenic technology. You can store it as liquid nitrogen, but this requires for you to go to temperatures of minus 200 degrees centigrade. So you have to go to such low temperatures to make liquid nitrogen and then be able to transport it at the pressures and temperatures. And then the more interesting ways where we can do research and improve upon is absorption. So if you can have hydrogen to absorb onto something like carbon nanotubes, metal organic frameworks, or metal hydride materials. So this is where the research is happening. So people are looking at what materials we can use to store hydrogen. So if you can use that material, store hydrogen, absorb hydrogen, then you can transport it somewhere and take it out and use it. One of the advantages of this is high safety, because if you have absorbed hydrogen, it will not catch flame as easily as in the case of liquid hydrogen or gas cylinders. Okay, so the safety aspect here is a challenge, the liquid nitrogen or gas cylinders, whereas the absorption, or when you're talking about materials, the safety is inherently improved. So that's why we are looking at to see if there are any materials that will serve that purpose or help us. So here, but the downside of it, so you say, this is more high safety, right? I'm talking about high safety when you absorb it. But what is the inherent problem with it? You have to, in order to extract the same hydrogen, you have to go to higher temperatures. So for example, liquid nitrogen is stored at minus 253, right? So you don't need any more energy. As the temperature rises, the hydrogen comes out. Cryo absorption also at minus 200. So if you look at metal hydrides, it happens in the room temperature range. So that's why these are very interesting. The most interesting things, the hydrogen storage materials are metal hydrides. Then compressed hydrogen, other metal hydrides, water, the temperatures go up and up and up. So water, if you see, it's a very stable molecule. So in order to break it, just in terms of temperature perspective, it has to be 1000 degrees or more. So what the inherent problem is, sometimes we talk about surface absorption, but the release of it might be, you have to spend a lot of energy to release it. So that is something you need to keep in mind. So as it stands today, I think metal hydrides, interstitial metal hydrides, are the way to go to store hydrogen. If not for liquid nitrogen, I think the best ways as they stand today are liquid hydrogen, if you can transport it that way, or in cylinders in compressed format. But if you want to use a solid material and improve safety, it is interstitial metal hydrides. Okay, and I think the last one, I think in the energy storage thing, so the chilling technology. So I think this is something that you might not, I don't know if you have paid attention, but a lot of big buildings have this technology. So what you have is cold water running from top to bottom or bottom to top. And then, each floor there is something called a air handling unit. So this building cooling or chiller technology has three main units. The chiller unit, which is located at the bottom in this figure that I'm showing you, the cooling tower located at the top, and then air handling unit. These are in each floor, for example. So what is happening? You are running the cold water through each floor. And in a simple term, what happens? You have air in that floor. So let's say it picks up some air from your room, which is at a higher temperature, and then it goes through this air handling unit, exchanges that heat with the water, and the air comes back colder and blows at you. So essentially you are getting cold air in that manner. So hot air is going, exchanging heat with water, it's then coming to you as cold air, and that's how you feel the cold air. And then the water, what is happening? Water, it is absorbing the heat from the air, and water goes from room temperature or very low temperatures to high temperatures. So there is the water cooling happening somewhere else in that system. Usually in the cooling tower system is where the water cooling happens. So that is another energy storage technology that we employ quite a bit now, right? Every building uses this chiller-based technology only. If you look at any big buildings, they use chiller-based technology, and this is very predominant in a lot of locations. So this is another energy storage system. Okay, so if you look at some of the, so whenever we are talking about energy storage systems, okay, I think I'll try to wind it up in the next few minutes. then we have time for questions. So whenever you're talking about energy storage systems, you talk about some terms like specific energy and specific power. That's one thing. I also referred to this earlier, right? So what does specific energy mean? So it's defined as either per unit weight or per unit volume. You can say gravimetric energy density or volumetric energy density. But what does it mean? It only tells you how much energy is contained in that system, the total amount of energy, like a bottle of water in this case. It's the total energy contained in that system. It doesn't tell you how fast or how slow you can extract the energy. So that is specific power is the one that tells you the same thing. So if you are pouring water, for example, the rate at which you can extract energy. So that is watt per kg. So this is specific energy and power are very important when you are referring to any energy storage system. Energy is the total energy content. Power is how fast you can extract it, how fast or how slow you can extract it. So if you go back, so these are the, I listed several things here, for example. So I think several battery systems. So I think if you go back and look at this slide, I think you can get more information. I'm not going to go through those details. That is just a collection of data there. Okay, and here, so we are looking at specific energy, million joules per kg, and specific gravimetric energy density per kg and volumetric energy density per liter. So why is this important? For example, if you take a car, even if you have very high specific energy density per weight, which is the gravimetric, if the volumetric energy density is very high, what is the problem? You need a large volume to be accommodated, which is very hard to accommodate in a car. So if you are looking at a car, you want very high specific energy density or gravimetric energy density as well as volumetric energy density. But whereas if you're looking at a ship, for example, you are not worried so much about the volumetric energy density. So volumetric can be high, but ship can accommodate that kind of volumes also. So you are more interested in the weight part, for example. So you don't want to add a lot of weight, volume is fine for a ship. So essentially, so the reason I'm putting it out here is you need to, I think these are the terms that should be familiar, that you should get familiar with to kind of understand what it means. So if you look at this chart, if you look at liquid hydrogen, hydrogen gas and everything, the gravimetric energy density is very high. But because it's a gas, hydrogen is a gas, the volumetric energy density is very low. So if you want to use it in a system where volume is very important, it's not very good. And this second set looks about our regular fuels. Okay. So if you look diesel, petrol, kerosene, various things, sugars in your body also. So they are reasonable energy, gravimetric energy density, reasonable volumetric energy density. And if you look at metals, so aluminum, for example, so you see, even though it has a low gravimetric, volumetric is very high because metals are packed very high density, right? When you talk about a metal, they are very high density. So volumetric energy densities are high. And then if you look at our man-made or these technologies, they are on the lower side. So this is why we are trying to jump from here to here. That is the whole idea in learning these things and understanding these things. And Ragone plot. So this is the same thing, specific energy we talked about and specific power I introduced, right? Energy, specific energy is the amount of energy contained like a bottle of water. Power is how fast the energy can come out. So if you see, batteries have high specific energy but low power, whereas capacitors on the other side, high power, low density, low energy density. I talked about it when I introduced batteries and those things. Whereas flywheels, compressed air energy storage systems, they fall here in this range actually. Good power and good energy. And if you look at hydrogen, gasoline, they are high up. So they have very high energy density and power also, both. Okay, and so I won't go, I think, quickly finish this. I think when you look at energy storage, applications are there, portable applications, vehicular applications we have. You can use it in various things. One thing to keep in mind when you talk about energy storage, the scales are important. For example, if you are talking about mobile scale, you are talking about 100 watts of energy. Generally, if you're talking about single home or a few homes together, 50 kilowatt. If you're talking about a small area together, 1 megawatts to kind of thing, and then grid scale, which is where you are producing and distributing energy. So the reason I talk about scales is that all the scales can have different good energy storage technologies. So for example, here lithium ion might be good. Maybe here it might have more challenges. So lithium ion, whereas lead acid might be better here, or compressed air can be better here, whereas here it will not be very good. So I think the point being, I think you have to understand the scale of energy storage to have the right kind of chemistry, right kind of technology come into picture. So you need to be very careful when you're referring to these energy storage scales to kind of assign the right energy storage technology to that scale of energy storage. Okay, so that's different scales. And final slide, I think we'll end with this. So I think this is something I think I always think about whenever I do anything. I think about it, and whenever I do, I think everybody should think about it. Is we can do a lot of fancy research, but at the end of the day, if you do not have these materials or this kind of awareness that if the materials are existent in our Earth's crust or not, then it's a challenge. So, for example, if you look at India, I know we are driving. I am a electrochemist. I work on batteries along with several other things. But one of the things that is not taken up at a high scale is exploration of lithium. So as it stands today, we don't have any lithium deposits. So we want to do lithium ion battery, but we don't have any lithium deposits in the country. So again, it goes back to the same thing. We have to import it from somewhere. So most of the lithium deposits in the world now exist in only two places: one, Chile, South America, or China. Same thing, some of the other cathode side materials, some of the other battery materials also, it's similar. We don't have cobalt. We don't extract cobalt at all. We do very minimal. So I think in order to be able to make our dream a reality, some of these have to be taken up. Some geological exploration needs to be done, all around India to see if we have lot of deposits of lithium, lot of deposits of other materials that are required for electric vehicles to kind of, become a large scale entity. So similarly, even if you're doing any, I think if we are doing any kind of research also, I think we always should look at the availability of the materials. If you are working with the platinum, palladium, rhodium, and some of the rarest of the rare earth metals, it's always a problem. We don't have enough. It's expensive, so it can never be transformed into technology. Yes, you can look at them from science perspective. You can say, okay, this is very interesting to understand the science behind it. Yes, you do it, but technologically that won't be helpful. So if you want to look at some aspects which can be technologically very attractive, you have to make sure that they are cheap, in the sense inexpensive, available in the earth quite a bit, and then we have enough deposits of the same. On that note, if you look at lithium is as good. I mean, it's as good as copper, zinc, manganese. If you look at this, the line I'm drawing, so lithium is, more than the availability of lithium is more than copper and zinc in the Earth's crust. Not in India, as far as we know, but generally it's highly available. So lithium-ion batteries, yes, it is a way to go. You don't have to worry about lithium shortage. As you see some of the articles, I think there is enough of lithium to make lots of cars. That's not a problem at all. So lithium availability is there. Okay, so with this, I think I'll stop here, and I think we'll have in the coming sessions. Today there will be introduction on solar cells, I think, in the afternoon, and from I think when we get to energy storage, you will see Dr. Martha and myself going into more details of batteries, more different types of technologies that exist in batteries, what are the challenges, what are the materials, and much more informative thing on the energy storage. And I think days 2 and 3, I think Dr. Santosh and his team will take care of all the solar cell related topics.
Thank you, Dr. Praveen. We can start taking the questions now. Okay, Chinmay or Vaibhavi, please start reading out the questions from the WhatsApp. Once we exhaust all the questions which are given in the WhatsApp group, we can start taking the questions. by raising the hands.
Okay, Praveen sir, firstly, I want to say it was a very interesting talk. So there's a question from Dharma Prabhakaran sir, assistant professor from Syed Amal Engineering College. So he asks, how can we manage power source for electric vehicles?
So I think the power source from electric vehicles. For example, a simple combination would be a supercapacitor plus a battery. So even in your regular cars, I think there is a supercapacitor component there. Sometimes it's there, sometimes it's not there, depending on what the cost of the car. Expensive ones have it, but in a general setup, we can have supercapacitor which can help you with the starting of the car when you are igniting the car engine, or when initially that high power discharge is required. So you can have high specific power is required. You can have a supercapacitor component in there. And then the battery, the lithium-ion battery or whatever technology that is existing can actually supply the energy in a steady manner. So once you go to 20-30 kilometers per hour, or let's say 60 kilometers per hour, there is not a big variation, right? You go between 60 and 80 most of the time. So then you can, that energy from the battery will be more reliable and it will be more continuous. So initially when you have acceleration starting of the car, the supercapacitor can play a role, and when you get to that 60 to 80 kilometer per hour zone, I think the battery in the electric vehicle can play the role. So it has to be a combination of the both. So I think if you take a simple battery, it will not be able to sustain the high specific powers when you require what you require at initial starting point plus the acceleration.
Okay, thank you, sir. So Anuj Raturi has a question. How can coal mines be used for methane generation?
So I think they need methane generation. They need to have methane. So I think we cannot just say that all coal mines will have methane. And I think when they're extracting coal now, I think it was not the case maybe a long time ago, but now I think they make sure they already measure if there is any methane. So for example, if somebody is going for core exploration or they're digging the coal out, there is any methane there, that is already extracted. So that methane is kept separate and used as a natural gas source of energy, and then the coal comes out. So initially when the geological exploration is happening, for coal extraction, the methane is kind of taken care of now, because I think, like I explained, the methane can warm the air much more significantly than CO2. So I think it is now very, I think all the countries have a very strict guidelines on the methane part. So even India does. So I think you have to be very careful when you're looking at any coal exploration. You need to make sure that all the methane is not simply going out to the atmosphere, but rather collect it and keep it in some form to kind of use it. So coal comes next. So in a way, I think the question, I think when you are extracting any coal, you are extracting natural gas before the coal exploration can happen, to kind of keep it contained.
Thank you, sir. So Shreya Tiwari asks, why is there such a drastic change in the electricity generation efficiencies between new and old plants?
New and old plants. So it's all to do with mechanical. Anytime that what you see, for example, if you look at your, I think a simple example will be the brake of your two-wheeler or a four-wheeler, right? That deteriorates with time. So if you have any mechanical component, what it does, there is friction that happens each time you're using it. And with that friction, there is some disintegrity in the material that's happening. So any mechanical system that you use typically over a period of the time will start losing its efficiency, or will start going down in efficiency. So essentially that is what also happens in a power plant, because there's a lot of mechanical components there. Things like, you have to produce steam, and that whole combustion chamber, and after that, use the steam to rotate a turbine. Turbine components are all mechanical in nature. So all that, what happens is, you are losing efficiency here and there, now and then, and so on. Over a period of 30-40 years, you see a drop in the capacity from let's say somewhere in the 45 range to a 30 range. And it is also not as simple to kind of say, okay, I will replace it and redo it. So it will incur a cost which is probably 70% of what the original cost was if you want to change all that setup. So so it has to be like a you have to look at it as situation where you have to look at both the costs, how much efficiency is going down versus how much it costs to replace it. So you have to have a trade-off between the two. So in order to be able to come up with what you want to do after, let's say, 10 years, 20 years or 30 years of time frame. But the main reason there's a significant loss is because of the mechanical components involved.
Okay, so the next question is from Rashmi Mohapatra. Is there any compressed air energy storage implemented in India?
At least I'm not 100% sure on that, but I haven't come across any in India. I doubt if we have any because I have not read about it anywhere. So we have nuclear. I know that because there's a Russian companies that are setting up nuclear plants for us in Tamil Nadu now. I think they are going to start a third one now. I think 2 of them are commissioned in the last couple of years. I think third one is being worked upon, or they started ground. They broke the ground, I think, a week ago or this week, sometime like in the last week or 10 days. So I think there's a third plant that the Russian, one of the Russian companies is helping us build. So I've seen nuclear happening over the last few years. Solar, we are happening. A lot of projects in solar are happening that I've known, but I haven't come across anything that relates to compressed air based energy storage. But I mean, I would be 90% sure, but there's still a small chance maybe I haven't come across it. But I think most likely no is my opinion.
Okay, so the next question is from Harshita Singh. Sir, like you said, ethanol has many advantages as a fuel, and we know it can be produced from sugarcane bagasse by fermentation. Why don't we focus on its production mainly as India produces significant amount of sugarcane?
Yes, so I think the government's goal is also the same from what I understand in the policy. Is because we do produce a significant amount of sugarcane. We want to produce ethanol from sugarcane. It can also be produced from other sources like rice can be used. One of the other predominant sources, so there's a division between countries in the world, 2 divisions primarily, one produced from sugarcane, one from corn. So I think there are some countries like US and others which produce from corn, whereas we produce from sugarcane. So those are the 2 primary things. But you have to keep in mind, sugarcane consumes a lot of water. So one of the things I didn't, in the lack of the time, I didn't talk about I didn't introduce that in this lecture. But if you go back and look, I think water, air, and energy are interrelated, are very much interrelated. And I think now I think a lot of the research work in my group, for example, happens in that context. I put water and air always in the context of energy. The reason being, the reason I brought it up here is that if you look at sugarcane, if you look at Maharashtra Beed region, where sugarcane has been produced left and right for the last 10-15 years, they are deprived of any water in their Earth's crust. So if you look at Beed region, I think typically they depend 100% or close to, very highly, I shouldn't say 100%, but very highly on rainwater for any kind of water. So they are a significant sugarcane raising region in our country. So what does sugarcane do? It consumes a lot of the water. So your groundwater is depleted. So that's the challenge with sugarcane. So I mean, I am not an expert in that area, so I mean, I have to spend more time to understand it better. But looks like sugarcane is not a good way to go, especially in country like in India, where we have a huge population and we have a huge requirement for water. And predominantly India is still dependent on monsoons, the 3 to 4 month period of monsoons for water availability. So it has to be a very careful and concerted effort if you want to go the ethanol direction. So I think it's not as simple as that. In thinking that we can raise sugarcane and produce ethanol, no, the water will be a big challenge. You will not, I mean, in a way you can think of it as shortage of water for drinking and other purposes. So that's the challenge there. Whereas corn, slightly better in that context. It's not a whole lot better, but slightly better in that context, because corn consumes, from what I understand, what I know, corn consumes less water than sugarcane. So the whole idea is that, you know, more agriculturalists have to come into picture to kind of help the engineers you know, figure out these things. So it has to be a more concerted interdisciplinary effort that needs to be made, that requires to be made, to kind of understand, let's say, if you want to go the ethanol direction, what is the best plant, or what is the best material in terms of plants to kind of go that direction, which consumes comparatively less energy but gives us enough ethanol. It also depends on how much ethanol you can generate. So you cannot just say we can take any plant and we get high ethanol. So that also differs. So it all depends. So it has to be a more concerted effort. It won't be a straightforward answer in thinking that, I think in using sugarcane, I don't think it's the sustainable solution in a long run. Okay, for the next couple of years, since we already have a lot of sugarcane around, yes, we can probably do it next 2 to 5 years, let's say. But it cannot be a 100-year solution or a 200-year solution for ethanol production. It has to be a more concerted effort to kind of figure out what exactly to do, how to do it, keeping in mind that water is very important.
Okay, so Anuj Raturi from Graphic Era deemed to be university is requesting for some enlightenment on aluminum batteries.
Oh, so aluminum batteries, I think it's not an easy thing. The reason is that lithium, if you look at lithium, it's a one electron battery, right? Lithium goes to lithium plus 1 electron. When you go to aluminum, aluminum is 3 plus 3 electrons. So it's not easy to tame. I think there is some research being done, but the problem is, how do you extract very efficiently all the 3 electrons and get it to aluminum 3 plus state? So that's the challenge. So inherently, when you have multiple electron involvement in any reaction, there's a challenge. So how do you control it? How do you tame it well to extract? See, even though it is giving 3 electrons, if you are physically only extracting current that is pertaining to less than an electron, then there is high inefficiency exists. So those are all the, I mean, that's a, I think aluminum ion batteries, aluminum based batteries is something that has, that is not well understood. So what I would say, if somebody is interested in getting into an aluminum ion based battery, so you can look at a 20-year career in that. So it's still in the very budding stages. So the challenges are there, significant challenges. How do you extract all the 3 electrons? Second thing, what electrolytes are necessary? See, the same liquid electrolytes that are used in lithium and sodium based are not helpful in aluminum ion. So aluminum ion coordinates very differently in comparison to lithium ion or sodium ion. So even between lithium and sodium, there's a significant difference on what electrolytes can be used, how that whole process works. So aluminum is even more challenging, significantly more challenging than these two. So yes, I think it is not understood to a large extent. A lot of people have to, for example, lithium ion started 20 years ago or 15 years ago, 2005 or so, I would say. And then now we have a good understanding of where it stands. So something similar has to happen. So if you want to think about aluminum ion based battery, I think if you start now, another 10 years, 15 years later, you might have something that might be promising at least. So that's where even lithium ion as it stands today, we only can use it in portables, right? The electric vehicles is still there, but expensive and all, whatnot. It's not to the extent of combustion engines. So I think we have a long way to go to make electric vehicles on the extent of, combustion vehicles, right? So that is where we stand in lithium ion. Sodium ion also fairly well understood, but aluminum ion comparatively very little understood. So you can start off as a research area, as your research topic. If somebody is interested in that research, they can start now, and maybe 15 years down the line, you might be a champion in that area. So that's where it stands as it is today.
Thank you, sir. That I think that's all from the WhatsApp group. If anyone else has more questions, please raise your hands and you can unmute one by one when your names are called and ask your questions.
I think everyone is waiting for the lunch. Sorry.
Yes, I think it's a long
Yeah, it's a
morning
long
session.
day, but I think we should all thank Dr. Praveen for giving such wonderful overview of the entire field of energy storage. In fact, he has started from very basic and lot of things which we might have heard here and there are nicely put in a very logical and chronological way. So I think this really gives the introduction to the next coming subsequent talks on the battery technology. So all the battery technology courses talks are planned during the day 4 and day 5. So please remember whatever is talked here, and the next talks would be continuation of the talks where continuation of the ideas and topics and concepts what Dr. Praveen has introduced at least today. So with this, we thank the speaker. We assemble again at 2:45 for the talk on the solar cell technology by Dr. Ishwar Murthy of AIRCI Hyderabad. So please have quick lunch and join us. We would like to see the same number, or if not more, to join back. We started from 120 and I think right now we are somewhere around 110. So I'm happy that the number is maintained throughout the day till now, and we hope you come back after lunch and listen to the talk on the solar cell. Please, let's go back and have lunch. Come at 2:45 and start the next session. Thank you, Praveen. Bye.
Okay, thank you.